Hi, everybody. I'm Chloe Widman, and I'm from Brown, but this summer I was doing research in the Lozert lab under Dr. Lozert, and this summer I was investigating subcellular steering with optogenetic neutrophils. And so to start from the end of the title, what are neutrophils? So first things first, they're innate immune cells, which means they are on your first line of defense against infection and all sorts of things that come with microbial invaders. And they respond by migrating towards chemical stimuli, as well as eliminating microbes with three different techniques for eliminating microbes. So here, I just have a little animation of this important response, which is migration to chemical stimuli. So when that chemical signal is detected by the neutrophil, it then begins the process of actually motivating and recruiting towards the infection site, which is sort of what I want to investigate with my research. So how do they migrate? Well, these chemical signals that they receive trigger excitable networks within the cell, which prepare it for migration by changing its shape and deciding a front and back of the cell and even more processes than that. So what these actually look like when they are excited, these networks, is something like this. So here we have a fluorescently marked wavefront, which is on the timescale of a couple minutes. And you see the one that I'm interested in is starting from around right here, and it has sort of an arc shape as it moves up to the top right of the cell. This is actually a model cell that we'll come back to talk about later. So I talked about steering. How do we actually go about steering these waves? The answer is with optogenetics. What optogenetics is using light-sensitive proteins to create activation switches within a cell. So when you use light exposure, you increase these proteins' binding activity, which prompts their excitation. So here we have an actual model of an optogenetic stimulation technique. And that little blue sort of beam you see right there is the light stimulation. These are these proteins that have been optogenetically tagged, or these proteins along with these sort of other proteins, then bind together as a result of the light signal. So if we can control the shape and position of the signal over time, we can drive these waves around a cell. So that's what I did. I built a system to create and control this light signal. And I use laser light because I want to work with parallel light, which we know laser light is collimated. That's one of its important specific features. And all of its light is one wavelength. So we need a specific wavelength to trigger our proteins. And that means that we can select that one specific wavelength with laser light. So here's a little diagrammatic explanation of my setup. So I start with the laser source, and I have my initial beam. And then I use some optical elements to sculpt and resize the beam. So my first element is a beam expander, which in my case, magnify the beam by 9 times. And this is just an amalgamation of 4 different lenses that I used to create a shape increase. I then used a mirror to reflect the light into a spatial light modulator, which we'll talk more about in a second, and then directed the light into a CCD camera. So this spatial light modulator is important because it's what actually does the sculpting of the beam. And how does that go about? How does the spatial light modulator actually work? It uses strategic phase delays within the laser beam to create interference. So there's a liquid crystal layer that lives right on the surface of the SLM that can fluctuate in time. So that's my example of the liquid crystal layer. You see all these little small individual pixels that actually we have control over in a pretty discrete way. Nearly every pixel we have control. And we start with a beam of light that is a wavefront. As we know, light is a wave. So when different regions of the input beam reflect off of different liquid crystals within the SLM, the wavefront is then changed. So if we have a parallel light wave input that then goes into the liquid crystal and diffracts off of it, we have a modified light wave output. So I want to be able to create novel output patterns to actually drive these processes how I want to study them. So I'm going to show you a very simple example, and then we'll expand on that in a second. So if I want to target a very focused output light, so if I'm taking a sort of defocused beam and I want to sharpen it, what I can do is tell the SLM to display this pattern. So this is actually a representation of what the liquid crystal arranges into. And these dark pixels represent where the liquid crystal is further laid back into the surface. And the lighter pixels represent closer pixels out to the edge. So when it's further away, you have a longer phase delay in the light that passes off of it. And when it's closer up, you have a shorter phase delay. And the result of this light is that we start with a defocused beam, and again, sorry for the contrast, but really you can see that there's really nothing much going on up here. It's just kind of a bunch of blurs. And this is actually an experimental result that I have. When I applied that phase mask, which is the pattern that I put in the SLM, you go from this defocused just array into a focused point. And so if we can do that with points, we can do that with larger shapes as well. So theoretically, I have this system that can shape and control light and time, and I want to use it to target images, to target shapes that match cell wave patterns we've seen. But I actually have to go about testing that because there's lots of things to calibrate within the SLM. So what I did is I built patterns to match this sort of wave that I pointed out before that starts as a band and moves towards the upper right of the cell. And this is the actual target pattern that I created. So I went in, and this is very simple. I just drew these patterns like in Illustrator, printed them out, and created an animation. I then computed these holograms, which are the actual patterns that I used to display on the SLM. So this is actually the sequential pattern. And what you'll notice is these patterns, even though the images look quite a lot alike, these patterns change very, very wildly from frame to frame. And that's a result of lots of complicated calculations, but it's just an interesting thing to point out. So once I actually displayed these on the SLM, I produced this output, which looks really great. It actually matches the target input that I had. And just to show you, here's my overlay as with the target image, just to see how well it maps. The one thing you might have noticed actually in my output animation is that there's a brightness fluctuation. So if you focus on one of these dots, you can see that over time it sort of starts to dim and brighten, which we noticed and we were like, okay, well, maybe this is kind of a problem because we want to stimulate neutrophils over the time frame of a couple seconds. And if this looks like it's happening on the frame of a couple seconds, we might not be able to stimulate them continuously. What we noticed is that even though you see this discrepancy at very short exposure, it is practically resolved over even a 20 millisecond exposure. So when I actually stimulate them for a couple seconds at a time, the light is practically continuous. So this is not going to be an experimental barrier for us. So we have successfully developed this system, which is very exciting. But what do we want to do with it? We want to see if we can model different characteristics of these excitation waves. So one of them is we want to control speed, or we want to see if we can control the speed at which excitation waves travel. We want to see different novel characteristics about the annihilation of these waves. And we want to see how stationary point stimulation, which is what optogenetics has done previously, compares to stimulation of moving regions. We also want to see novel things like if we can change the shape of these bands, if we can create novel chemical signals that we can use to study new things about neutrophils. So how are these useful? Well, to come back to the beginning, neutrophils are immune cells. So characterizing them helps us better understand the immune system's inner workings. And this optogenetic tool can help us do many more things with cell research and open the door for even more exploration. Thank you so much for listening to me, and thank you so much to my mentors.